Hello everyone, welcome back to Applied Thermodynamics subject. We will continue our discussion today about the Weber and combined power cycle. Today, first I will introduce you what is cogeneration and uh, why it is useful. Then we will continue our discussion with the combined power, combined Weber and gas power cycle. So let's begin with the cogeneration, with definition of that and why we are using this concept is uh, cogeneration. Let me just review what we had for the Weber power cycle and the main component of that Weber power cycle. If you remember, we had four main components for Weber power cycle as pump, boiler, and if you remember, let me just show something simple here. We had boiler, here, here condenser, turbine here, and also we had pump here. Let me just show it with pump here. If you remember, we had something like this. And we had Q in for the boiler to increase uh, thermal energy or temperature or heat by using heat of the working fluid, which was water. So the energy which is required is in this place, and usually we provide this energy from different sources like coal. By burning off something, we can produce heat or thermal energy, then increase temperature of the uh, water, then it phase changes from liquid to the gas and so on. So we need energy here. And in different plants, usually we use different type of fuels like coal, gas, and so on to produce this energy and increase the temperature or thermal energy of the working fluid or water here. So how we can reduce the required energy for in the boiler to increase the temperature of the working fluid in this cycle, this Rankine, ideal Rankine cycle. As you know, in many industry, the we need also to use heat in that industry. Like in food and beverage, we need temperature or heat for drying, washing, and so on. And also in chemical industry, we need uh, heat source or heat in this range of temperature, and also in textile industry. So you can see this is just some examples for different industries and area of the application of the heat or thermal energy in that industry. So you can see here also we need heat in this cycle. But let's see, in this Rankine cycle, what we had, we introduced Q in here, then it goes through the turbine, then here we had Q out. So for example, we introduce 100 units of the energy here, thermal energy here, and we just use produced work here. Uh, for example, it depends on the efficiency of this Rankine cycle, but just a few amount of this energy which is given to the cycle as Q dot in was converted to the W dot or useful work of the cycle. If you remember, we had also in different examples the efficiency was about 43, 34% or even higher 34%. How we can increase this efficiency? One way is to use, for 43% means just 43% of this Q in is converted to the W dot turbine, or W dot turbine minus W for pump. So most of the energy which we give to the system is wasted as this form Q dot out, as heat which we should get from the working fluid by condenser, which is waste of the cycle. But as you can see here, in this industry, we need heat source. We need this heat source, this heat for different purposes. So if we use this Q dot out for a heat source for this different process, then we can improve the total efficiency of this cycle. We call this cogeneration. Let's see some example. This, here is just a simple example of what I told you. Q dot in to the boiler. Then this Q dot in, this is in for that process. As I told you, for example, for drying, we need to have a cycle like this. We need to have a boiler, then introduce this Q into the Q dot into the boiler. Then this increased temperature will go to the process heater, or Q dot P. Q dot P is the process heat and pump. We need this cycle for these purposes, drying and so on. But if we can provide this temperature which we need for the boiler in this process, or directly for this part process heater, we can save lots of energy for this cycle. This waste can be input for this cycle. So cogeneration is the production of more than one useful form of energy, such as process heat and electric power, for the same energy from the same energy source. Like what we can have here, we can produce electricity by turbine, and also we can use its thermal energy, or Q dot out, in the process heater. So we can have something like this. This is an ideal cogeneration plant. As you can see in this figure, we have boiler and turbine, and usually instead of this process heater we have condenser. This part, it is still like a Ida Rankine cycle. We just replace the condenser with this process heater. Instead of the waste of the thermal energy in the condenser, we have this process heater. We give the high amount of thermal energy of the steam after turbine to the process heater. So you can see here we have electricity, and here we have process heater, or Q dot P. I can show like this. So the Q dot in will be converted to the electricity and Q dot P. So according to this configuration, we can define a parameter which we call the utilization factor. It means how much of the energy which is given to this cycle is converted to the useful application, for example, electricity or process heat. So E dot U, or utilization factor, can be defined like this: network output, which we have electricity here, for example, and process heat delivered, Q dot P, divided by the energy which is given to this cycle, which is total heat input, or Q dot in. We have Q dot in as input, and these two work, electrical work and process heat. So this equation is the utilization factor, or we can simply write like this: utilization factor equal to 1 minus Q dot out divided by Q dot in for a cycle. In ideal condition, without any loss of the heat or thermal energy from the pipeline, in or without any heat loss from the boiler or turbine and other equipment in the this cycle, the utilization factor will be 100%. All of the energy which is given to the system will be converted to electricity and processed. But due to that waste of energy in the pipeline, due to the lack of the 100% installation and also in the boiler and other equipment, usually the actual utilization factor is about 80%. However, in recent year, by some development in the material or in the configuration or in the installation of these equipments or pipes, this utilization factor have increased, and we have even more than 80% utilization factor for this cycle. And you can see here, compare this utilization factor, which is more or less something like the thermal efficiency. You can compare this with the thermal efficiency which we have only for the Rankine cycle without this processing. Here, 80% of utilization factor means 80% of the useful energy which is given to the system is being used for useful purposes, electricity and work. So you can see here how we can use this system cogeneration to use better and more efficient of the energy which we have and which we give to the cycle. That this cycle, this cogeneration cycle, which you can see here, it is just a simple and basic cycle for a cogeneration plant. Usually we don't have something like this. It is a little different from here. If you notice here, all of the steam which go to the turbine will go to the process heater. But usually we don't need something like this. Imagine we have a factory, a plant, and we need and we use a steam uh, cycle to produce electricity in that industry. So, uh, but usually we don't need 100% of the electricity. And sometimes we may do not need this process heater in the system. For example, the drying line is off for some while. So what we can do is to put something like this configuration. You can see differences between this and previous one. We add this expansion valve. As you can see in this cogeneration plant, which we call that cogeneration plant with adjustable loads, we have different modes. First, at times of high demand for process heat, here, all the steam is routed to the process heating units and none to the condenser. It means here, uh, M7 or we don't have any steam from turbine to the condenser. So we have only this line. The whole steam will go to after turbine, and also from this well will go to the process heater, and the condenser is out of the cycle. In this mode, the waste heat is zero in this mode. If this is not sufficient, some steam leaving the boiler is throttled by an expansion or pressure reducing valve to the extraction pressure or P6 and is directed to the process heating unit. So initially in the cycle we have something like this. This is closed, and we have a boiler here. It will go to the turbine. After turbine, it has two branches, and this is a normal condition when we don't have high demand in process heater and also for the turbine. So it go to the turbine, then process heater, and also condenser and boiler, and we have this cycle. Both of the process heater and turbine are in the cycle. When we have high demand of the process heater, we close this. So whole steam which go to the turbine will go to the process heater after turbine, and we have only this cycle. And even it is not enough. I mean, the steam which go to the turbine, for sure its temperature will be lower after turbine. So the maybe the thermal energy or heat which we have required here in process heater may not be enough. So we have also a valve here which is closed up to this step. If we need the maximum amount of the steam to go to the process heater, we can open this expansion valve. So it will suck this steam from this line to the process heater. Then the temperature, here temperature uh, of the steam here, or here is T4, here is T4. After this will be T6. T6 is lower than T4. But if we open this line, T4 and T5 will be in same amount of temperature. Then the process heater will receive higher amount of the thermal energy. Maximum process heating is realized when all the steam leaving the boiler passes through this expansion valve or PRV. Then no power is produced in this mode. So in the maximum uh, for the when we need the maximum process heater, we will also close this and hold then this part will be out of the cycle in this case. And whole energy, we have only process heater in the cycle. And we do not produce any electricity in this case because the demand for the process heater is the maximum. When there is no demand for process heat, all the steam passes through the turbine and the condenser, and the cogeneration plant operate as an ordinary steam power plant. This is something opposite the previous step when we don't need any process heater or when we need high amount of the electrical power. Then we will close this line. We will close this line as well. So all of the steam will just passes from turbine and condenser. Then we have only a Rankine cycle or a sim or ideal or a simple steam power plant. So you can see here how we can manage this cogeneration plant with an adjustable uh, loads or with different loads to have both of the process heater and turbine in the cycle for different conditions. High amount of process heater, the maximum amount of process heater, when we don't need any process heater and we just need the electricity. You can see here how we can manage the flow of that steam to have these different modes in this cycle. And you can see here how we can calculate, as usual, for a cycle, we can write this equation Q dot in, which we have in the boiler, is equal to m dot 3, which we have here, mass flow rate of the steam to the boiler, times H4 minus H3, enthalpy in this point. Q dot out, which we have here in condenser, which is the wasted thermal energy of this cycle. This is only when we have the this condenser in this cycle, then it will be equal to m dot, the mass flow rate in this point, times H7 enthalpy at zero point 0.7 minus enthalpy at zero point 0.1 before and after condenser. Q dot P, or the process heat, which we have in process heater, is equal to m dot 5 H5, which come to the system here, plus we have also in this line m dot 6 H6 minus what, the output of this process heater, m dot 8 H8, or enthalpy at zero point 0.8. As you can see here, this is for a general condition when we have the steam from both of these two lines. When we don't have any, when turbine is out of the cycle and it is not working, and the steam is routed from this line, then this 6 or m dot 6 H6 will be 0, for example. And also when this is closed, it will be 0. And the whole, you can use this equation to calculate Q dot P in different condition, which is dependent on the state of the working fluid. As you know, H, or enthalpy, is a parameter or properties of the working fluid, which is dependent on the pressure and temperature of the working fluid, and also its mass flow rate in that state. And the work which we can get from the turbine in this cogeneration plant with adjustable loads is W dot turbine equal to m dot 4 minus m dot 5, m dot 4.4 minus m dot 5. This is, if m dot 5 is 0, we don't have any mass flow rate of the steam to the process heater. This will be only m dot 4. Whole steam will go to the turbine. But because we sometimes we may have this branch open as well, then we should subtract this m dot 5 from the whole steam which come out from the boiler. So m dot 4 minus m dot 5 times H4 minus H6. M dot 4 minus m dot 5 is the amount of the, or mass flow rate of the uh, working fluid or steam which come to the turbine. And for the enthalpy here and here is important. And also we have this m dot 7 for the, which is the amount of steam which go to the condenser, m dot 7 times H6 minus H7. This m dot 4 minus m dot 5, it will come to the cycle, and it will divide it to different fractions, m dot 6 and m dot 7, and we can just write like this: m dot 4 minus m dot 5 is equal to m dot 6 plus m dot 7. All the steam which come to the turbine will be divided to these two. So simply we can calculate the, and if you notice here, the state of the steam in point 6 and 7 are identical. The temperature and pressure of the steam after turbine for these two lines will be identical. So H6 minus H7 can be calculated by their state as well. However, it depends of how amount of the uh, steam is routed to the process heater or condenser. Later in an example, we will see how we can calculate this W dot turbine in this cycle like this and so on. This is these equations are the equations which can be used to calculate the uh, W dot or Q dot P, Q dot out, and Q dot in of this cycle. By this information, we can calculate this utilization factor of this cycle as well, of this plant as well. Let's first see a video of how this cogeneration can be applied in a real plant or industry. Then we will see how we can use this Q dot in, Q dot out, and the other energy flow in the cycle by solving an example related to this cogeneration plant. Let's first see the video which is related to the cogeneration application in a real industry.
The manufacturing processes at the LANXESS site in Nagda meet the highest environmental, safety and health standards. With its new cogeneration plant, LANXESS is able to meet most of its energy demand for the production at its Nagda site.
We at LANXESS are always looking for opportunities to enhance our contribution towards environment. At Nagda Cogen facility, we generate steam and electricity in an eco-friendly manner, thereby reducing our carbon footprint.
To fuel the plant, the company uses soya husk, a waste product from the processing of soya crops. The biomass comes from the farmland within a radius of 100 kilometers around the site. We plant soya to sell the beans and benefit from selling the waste husk to LANXESS. The soya husk is transported over a conveyor belt into the bunker of the cogeneration plant and is burnt in the furnace. The heat is utilized to generate high-pressure steam. The steam is fed to the back-pressure turbine, which generates electricity for the production plant. The expanded steam of 12 bars and 6 bars gauge is used in the production processes as a heating medium. The flue gas generated during the combustion is treated in an electrostatic precipitator. The flue gas emission to the atmosphere is in full compliance with environmental standards. The combustion of biomass is CO2 neutral. The amount of carbon dioxide released during the burning process is the same as was captured in the crop's photosynthesis. Domestic wastewater is used for the steam generation. It is treated in the site's own facilities before it is used at the cogeneration plant.
With the new cogen plant, the operations at the LANXESS India Nagda site will be virtually 100% self-sufficient in terms of power. This will provide a great advantage in manufacturing reliability while lowering costs.
By commissioning the cogeneration plant, LANXESS saves around 70,000 metric tons of coal per year, which reduces emissions by 95,000 tons of carbon dioxide.
This initiative that uses biomass as a fuel is a win-win, as it not only is environmentally friendly, but also commercially viable.
The Nagda cogeneration plant is a pioneering LANXESS project, ecologically and economically.
LANXESS is deepening its roots in India and is committed to contribute to the sustainability of the chemical industry in India. This new cogen plant in Nagda is an example of our many green chemistry initiatives to protect the environment and to safeguard the well-being of the local communities.
Now, let's see how we can use the equation which I showed to you to calculate the efficiency or the utilization factor for a cogeneration cycle or an ideal cogeneration plant. First, consider the cogeneration plant, which is shown, which you can see in this figure. As you can see here, we have the main components, which we have the Rankine cycle, which is also the process heater is added to the cycle. We have boiler, turbine, condenser, pump in the cycle, and also because this is a cogeneration cycle, we have a process heater in the cycle, the expansion valve, the second pump, and also we have a mixing chamber here to mix the two different line for the working fluid come from the process heater and condenser. And if you notice, this is a cogeneration plant with adjustable load because we have expansion valve here and we can manage the flow and also flow rate from the of the steam after boiler to the turbine or to the process heater. Then steam enters the turbine at 7 megapascal. Steam after boiler in this point is entered to the turbine at 7 megapascal and its temperature is 500 degrees Celsius. Some steam is extracted from the turbine at 500 kilopascal for process heating. So we use some fraction of this steam which goes to the turbine. We use that some amount of that to the for process heater, and the remaining steam continues to expand to 5 kilopascal. What we have here after turbine is the waste or the remaining steam actually go to the condenser and the pressure is 5 kilopascal. Steam is then condensed at constant pressure and pumped to the boiler pressure of 7 megapascal. As you can see here, before and after condenser, you know the pressure doesn't change. It's the baric process. Then it will go to the pump. The pressure is increased to 7 megapascal, and it is sent to the boiler or mixing chamber, which is just a mixer. It will go again to the turbine, and its pressure, 7 megapascal, just its temperature is increased after turbine. At times of high demand for process heat, some steam leaving the boiler is throttled to 500 kilopascal and is routed to the process heater, like what we have here. It is in some times when we need to the process heat, then we will open this expansion valve and we just route this amount of the steam to the process heater. The extraction fractions are adjusted so that the steam leaves the process heater as a saturated liquid as 500 kilopascal. After this process heater, we have saturated liquid 0.7 and the TS diagram, as you can see here, and the pressure is 500 kilopascal. It is subsequently pumped to 7 megapascal. Again, we use a second pump to increase its pressure to 7 megapascal. So in mixing chamber, we have just a mixing of these two lines. Their temperature is different, but their pressure is similar. We use this mixing chamber to have a liquid in a common or equilibrium temperature, same temperature. The mass flow rate of steam through the boiler is 15 kilogram per second. So here, m for the boiler or m.11 equal to m.1 is 15 kilogram per second. Disregarding any pressure drops and heat losses in the pipeline and assuming the turbine and the pump to be isentropic. So here we have this assumption. We should also mention that when we are going to solve the problem. We don't have any heat loss in the cycle, and also in the pump and turbine we have isentropic process. Then we need to determine the maximum rate at which process it can be supplied. Maximum rate at which process it can be supplied means hold the temperature, go to the process heat, hold the working fluid actually. The power produced and the utilization factor when no process heat is supplied. It means this valve is closed, this is closed, and whole will go to the turbine, then condenser. See the rate of process heat supply when 10% of the steam is extracted before it enters the turbine in this branch, 10% for in this line, and 70% of steam is extracted from the turbine at 500 kilopascal for process heating. In this here also 70% after turbine, 70% in this line. So you can see different condition A, B, and C. When this is closed, this closed, or go for electricity production. When we this is closed, will go to the process heater, and when we have a fraction, just a fraction of the steam will go to the process heater when we have both of the turbine and process heater in the system. So let's see how we can solve this problem. And also you can see this plant in a TS diagram. We can see in these different states the temperature and entropy for this cycle. We can use this diagram also to find the properties for different states. Then we can calculate Q in, Q dot in, Q dot P, W dot for turbine, and also Q dot out, which we have in condenser. Let's see how we can find and determine the answer for part A, B, and C of the question. Okay, now let's see how we can solve this problem and find the answer for part A, B, and C of the question. Here again you can see the schematic and also TS diagram for this cycle, for this cogeneration cycle. This cogeneration plant is shown here. The maximum rate of the process heat supply, power produced, and the utilization factor when no process heat is supplied, and also the rate of process heat supply when steam extracted from the steam line, and turbine at the specified ratios are to be determined. This is according to the question which we should find for this cogeneration plant. First, let's see what should be our assumption. One, steady operating conditions exist. We can have this assumption, however, you already know about that. It means there isn't any changes in the, for example, pressure, temperature at each state, which also are shown in this figure with time. It means after, during this calculation, during the time which we are going to calculate these parameters for this plant, there isn't any change. For example, for state 1, it will be 7 megapascal pressure and 500 degrees Celsius temperature, and it doesn't change during this that calculation, during that process. Assumption number 2, pressure drops and heat losses in piping are negligible. we should have this assumption to be able to solve this problem. Without this, it will be very complicated to exactly find the loss, and also it is according to the question in instruction. And number three, kinetic and potential energy changes are negligible. However, we have in the real plant these losses, these changes in the kinetic and potential energy, but we can here for the to simplify our calculation, we can have this assumption. Otherwise, it is not that much easy to solve the problem. So with these assumptions, let's analyze the question. The schematic of the cogeneration is shown here and also its TS diagram. The power plant operates on an ideal cycle, and thus the pumps and turbine are isentropic. Pump means we have to pump in the cycle, pump 1 and pump 2, and you can see the process for the pump. As you know, pump in this cycle, in this plant are being used to increase the pressure for the working fluid, which is the steam or water here. For pump 1, you can see here the pressure before that is 5 kilopascal, after that is 7 megapascal, and the process is between state 8 and 9. And you can see here it is isentropic, and as you know, in TS diagram for isentropic process, it is a vertical line in the TS diagram. And also for pump 2, again we have an isentropic process. And also in turbine, which is 3 to 5, and also we have again an isentropic process. Then according to this graph, also you can we should find the properties for the different states in the cycle. This is what we are going to actually do. We should find the properties for different states, like what we had also in previous example. Then by finding the properties or enthalpies for the cycle, we can calculate the energy flow in the cycle, and we can finally understand how much is the efficiency of the cycle and so on according to the question. And also there isn't any pressure drop in the boiler, so pressure before and after a boiler is identical, 7 megapascal. And also same for the process heater, same for condenser, no change in the pressure. And also steam leaves the condenser and process heater as saturated liquid. Also it is important. You can see here before, after process heater and saturated liquid means state 7 and also state 8, and you can see here they are on the saturated liquid line. Then the work inputs to the pumps and the enthalpies at various states should be determined according to the characteristic or properties which we have. So let's start with the most simplest one. For the pump 1 and pump 2, we can calculate the work for these two equipment, for these two pumps, by this equation. It is familiar for you, I think. Specific volume of the working fluid to the pump times the pressure before and after pump will give us the work which is given to the pump. So W pump 1 in is V8, the working fluid to the, here V8 to the pump, or the specific volume of the working fluid to the pump times pressure after and before. Pressure after pump is state 9, and pressure before the pump is in state 8. So P9 minus P8. And we need P9 and P8, both of them are nouns of the question, and you can see here P8 5 kilopascal, P9 is 7 megapascal. What about a specific volume for 0.8? To find this specific volume for the working fluid, which is water here, we need to refer to the table for the saturated water in with this pressure, because we are going to find this. So pressure here is 5 kilopascal, and also we know it is saturated liquid. So we need to go to the thermodynamic table. I'm not going to go that. I think it is very simple for you. You can easily do that. We have already discussed about that enough, so you can go and do this by yourself. So if you go to the table, I think table A5, you can find a specific volume, or VA is VF actually in this point, and you can find V8, which will be equal to 0.001 005 meter cube divided by meter cube per kilogram. And do not forget to convert pressure to the kilopascal. P9 is 7 megapascal, which means 7,000 kilopascal. So by substitution and using this unity conversion, finally we can have W pump 1 in, which means 7.03 kilojoule per kilogram. So we have calculated the W pump 1 in. With same procedure, we can calculate W pump 2 in, or the work which is given to the pump number 2, again specific volume for the working fluid to the pump, or V7, time the pressure difference after and before the pump. After pump, the pressure again is 7 megapascal, before pump is 500 kilopascal. So we have P10, P7. What about V7? Again, if you notice here, we state 7 is saturated liquid. Again, here is saturated liquid, and pressure is 500 kilopascal. Again, we need to go to this table and find V7, or specific volume for water. So again, for table A5, you need to go there for this pressure for saturated liquid, or VF. We can find V7, which is this much, times the P10, 7 megapascal or 7,000 kilopascal, minus 500 kilopascal, which is P7. Using this unity conversion again, we can have W pump 2 in. Now we have W pump for both of the pump which we have in the cycle. Later we will see why it is important, because finally we are interested to have all of the enthalpies of the cycle. So we need to use this W pump to calculate some of the enthalpies in the cycle. Okay, state 1, 2, 3. As you can see here, 1, 2, 3, 4 are the states after boiler, and their pressure and temperature we have. And if you notice, these points, these states are in the superheated region. So we should go to the table for superheated region with this pressure and this temperature, and we need to find the enthalpy for the superheated water with this temperature and pressure, which is equal to 3,411.4 kilojoules per kilo. So we have enthalpies for these 4 different states. What about enthalpy at state 5? State 5 is after turbine. We have the pressure for that 500 kilopascal. But if you notice here, it is in the wet region or saturated vapor and saturated steam region. How we can find the enthalpy for this point? If you remember, we had that equation. The information which we have for state 5 is S5 is equal to S1 or S2 and so on. S3, which is identical. Then we have entropy for this point. Again, with same procedure, if you remember, we need to find the X, the fraction of the moisture in the mixture. Then by knowing the X with the equation, if you remember, was like this, for example, here we have this 5 minus G divided by SF. You can find X again, then you need to use equation for H, which H5 is equal to HF plus X HFG. Simply, you can find H5. With same procedure, again using these 2 equations, you can find H6. If you want to know how to calculate enthalpy for these 2 points, 2 states, you need to refer to the previous session and review the procedure which we use to find the enthalpy and entropy in the wet region. So by using these 2 equations, I'm finding X for H5 and also 4.6 or state 6, again S6 is equal to S5 equal to S1, for example. So we have S, then by this equation we need to calculate X for H6, and by using that, then again use this equation, and finally we can, and for this information SFG and HFG and HF, we need to refer again to the table which we have for table A5, and you can find HF and HFG for the, for example, point 6. For point 6, we also know how much is the pressure. So you can go to the table for the saturated water and find the HFG, HF. So table A4 or A5, here we have pressure. Then you can find SF, SFG, HF, HFG. Then using these 2 equations, you can find all of the, then you can find the H6 and also H5. For H6, you need to go to table A5 for pressure of 5 kilopascal. For H at stage 5, you need to find for H for pressure of 500 kilopascal. So by using this method, you can find enthalpy for H5 and H6. What about enthalpy at state 7? If you notice, it is on the saturated liquid line. So at state 8 is equal to HF. And what we also know about this point, or point 7, point 7 is after heater, process heater, and already I told you in the analysis that the pressure after process heater also will be 500 kilopascal. So we need to go to the, again, table A5 and find the enthalpy for the for this pressure for the saturated water. So saturated liquid, you can see here H7 also from table A5. We can find this HF. And H8 again, if you notice in the table, it is after condenser. We have saturated water again, and if you notice again, we need to go to table A5 and we can find HF for the pressure here is changed to 5 kilopascal. So we can also find H8 or enthalpy at state 8 for the saturated liquid at 5 kilopascal pressure, which is 137.75 kilopascal. So all of this information can be found in the table. Then what about state 9 and state 10? If you notice state 9, the enthalpy of state 9 can be calculated by this equation, because according to the definition, we know the change in the energy in the pump will be equal to the work in the pump. We had this equation in the previous example. We can write like this. H9 minus H8. The change in the enthalpy of the before and after or in the pump will be equal to the work which is given to the pump. So we can simply rearrange this equation and find the H9, or which is after this pump 1, and we can find H10, which is the enthalpy after pump 2. So we can simply again find H10. So now you can see how we can find we have already actually calculated and found the enthalpies for all of the states in this cycle. Now let's see how we can use this information to find the answer for part A of the question. The first part of the question was when the maximum rate of process heat is required. How we can reach that the maximum rate of process heat. The maximum rate of process heat is achieved when all of the steam leaving the boiler is throttled and sent to the process heater and none is sent to the turbine. In other words, just we have this after boiler, all of the steam is throttled to the process heater and all of them empty. The flow in here is 0, here is 0, here is 0, and also we don't have flow in state 8 as well. So only these part will be in the process, and the other parts are out of the cycle. In other words, M.40, M.70, M.3, M.5, M.6, M.3, M.5, M.6 will be 0, and M.4, M.7, which is after process heater, and this is after throttle, will be equal to M.1, or even M.2 is also equal to these 3. So all of the steam after boiler will go to the process heater. Then Q that Pmax, or the maximum process heat which we can get from this cycle is equal to M.1 times H4 minus H7. Why M.1? Because all of the steam is passing through the process heater. So M.1, which is equal to this the other M dot in the cycle, and H4 minus H7. we have here before and after process heater. So the mass flow rate of the working fluid to the process heater times the changes in the enthalpy of the working fluid in the process heater, H4 minus H7. Simply by substitution of this information, we know how much is m dot 1. It is 15 kilogram per second. It is given, it is noun of the question. And also we already have calculated and found the H4 and H7 for the example. So Q dot P max, or the process heat, maximum process heat which we can get from this cycle, is this much. The utilization factor here is 100% because no heat is rejected to the surrounding by the condenser actually. And also it is assumed there isn't any heat loss through the pipes or the devices in the cycle. Part B, it is for when no process heat is supplied. So in this case, let me just clear the part A. When no process heat is supplied, all the steam leaving the boiler passes through the turbine and expands to the condenser pressure of 5 kilopascal. In other words, here will be closed, and also here is closed. Then the cycle will be like this, to the turbine, then to the condenser. According to this, and it will do condenser, then pump 1 and mixing chamber and boiler. So in this case, M.3, M.6 and M.1, M.1, M.3, M.6 will be identical and will be 15 kilogram per second. M.2 and M.5, as I showed you, M.2, M.5 will be 0, no mass flow rate here, or no flow of the steam in these lines. All of the mass is introduced to the turbine in the condenser and so on. So in this case, we have a simple Rankine cycle. So the maximum power which is produced in this mode can be calculated by this equation. W dot turbine, it is simply like what we had for the Rankine cycle. W dot turbine is equal to M dot H3 minus H6. The mass flow rate to the turbine times the change in the enthalpy or energy of the turbine actually. H3 minus H6. This is the flow of the energy we have in this direction actually. H6 minus H3 minus H6 times M dot, which is through this. M dot which we have here is 15 kilogram per second. Again, we have H3 and H6, and also M dot. We can calculate W dot turbine out, and also we can calculate W dot pump in. For the here, if you notice, it is not mentioned which pump, but you should know it is for pump 1. Why? Because this part of the cycle actually it is out of cycle in this mode, and whole steam will go to the pump 1. For pump 1, we can calculate the W dot, which is the mass flow rate to the pump times the work which we have calculated in previous slide. If you remember, we have already calculated W pump 1 in. So W dot, we have calculated the W pump in, then simply by multiplication of the mass flow rate of the working fluid to the pump by the work in of the pump, we can calculate the power, or W dot pump in, which will be equal to 105 kilowatt, which is the power of the required for the pump. Then W dot net will be equal to the work which is produced by turbine minus work which is given to the, or which is the power which is given to the pump. So W dot net out, or the net power output of this cycle, is equal to the turbine power minus pump power, which is, we have both of them, and the final answer will be equal to approximately 20 megawatt of the power which we can get from this cycle. And Q dot in this cycle is in the boiler. How we can calculate that? Again, simply the mass flow rate of the working fluid through the boiler times the changes in the enthalpy of the working fluid in the boiler. Change in the enthalpy of the boiler, or energy of the boiler, energy of the working fluid in the boiler is H1 minus H11 times M dot 1. Again, we have H1, and also H11 we have already calculated in previous slide. Then we can calculate Q dot in, and we know all of the mass flow rate is to the boiler. So we have M dot 1, we have H1, we have H11. Then finally we can get this, we can calculate Q dot in to the cycle. However, if you notice, we didn't calculated H11 in the previous slide. Why? Because if you notice, H11 is after mixing chamber, and according to the structure of mixing chamber, it is supposed there isn't any changes in the temperature or pressure or the state of the working fluid in the mixing chamber. The purpose of this mixing chamber is simply to mix these two working fluid which we have here in the mixing chamber. So H11 here will be, as you can see also, H11 is 144.78. This is the amount of enthalpy which we have calculated for the 0.9, as you can see here. So the H9 and H11 in this cycle are identical, and they are equal to 144.78 kilojoule per kilogram. So simply we have also H11. Then by this equation we can calculate Q dot in, which is given to the energy which is given to the cycle. Now by this information we can go and calculate the utilization factor for this cycle. If you remember, we had this equation, epsilon sub U is equal to W dot net, or power, net power of the cycle, plus Q dot P, or the process heat, divided by Q dot in, which is the input heat which is given to the cycle. We have all of this information, but here the Q dot P is 0 because we don't have any process heater requirement. So in this case, the utilization factor, or here we can say thermal efficiency of the cycle, actually is 40.8%. Then it means 40.8% of energy is utilized for a useful purpose. Notice that utilization factor here is equivalent to the thermal efficiency, because we have only the Rankine cycle in the process, and we don't have process heater in the cycle, and we don't have process heater requirement here. Part C, In part C, we have a special case, which is usually also this cogeneration cycle is like that. A fraction of the working fluid or steam is will go to the process heater, and the fraction of that will go to the turbine. So this is what we usually have in the cogeneration plant. Neglecting any kinetic and potential energy changes, an energy balance on the process heater yields this equation. That in this is for the process heater, this part which we have. The energy balance for this process heater, it means the energy according to the first law of the thermodynamics. It adds into this system which I have choose here is like this. Idat in is equal to Idat out. All of the actually this is for process heater. All of the energy which come to the process heater should be equal to energy which rate of energy which goes out of the process heater. So the energy which come to the process heater is m dot 4 h4 this line, m dot 5 h5 this one, this is come to the system, and the energy which goes to the out of the process heater is m dot 7 h7, and also because this is a process heater we have q dot p out for the process heater. So this is the energy balance equation for the process heater. So by using this equation and rearrangement or restructuring of this equation, we can write like this: q dot p out is equal to m dot 4 h4 plus m dot 5 h5 minus m dot 7 h7. Why the m dot 4 and m dot 5? It was mentioned in the question in instruction that 10% of the steam which come from the boiler will be throttled to the process heater. So here m dot or mass flow rate of the steam here is 0.1 times the whole steam or mass flow rate of the working fluid, which we have here in that one, which is 15 kilogram per second. 10% of that means 0.1 times 15 kilogram per second, which will be 1.5 kilogram per second. So m dot 4 in this point is 1.5 kilogram per second. M dot 5 is well, it was mentioned that 20% of the steam or working fluid after turbine will be routed to the process heater as well. So as you notice here, the working fluid which come to the turbine is 15 kilogram per second. It is assumed that this steam go to the turbine, all of that, and we 70% of that is directed or routed to the process heater. So 0.7 or 70% times 15 kilogram per second means 10.5 kilogram per second of the mass flow rate or steam also come from this line to the process heater. So m dot 5 will be 10.5 kilogram per second. Then this, because of the conservation of mass flow rate for a system, all of the mass which come to the system by these two lines will be equal to the mass which go out by this line. So m dot 7 is equal to m dot 4 plus m dot 5. These two will be equal to this one. 1.5 plus 10.5 is equal to 12 kilogram per second mass flow rate in the point 7 or state 7. Then again, we can go back to the equation which we have to calculate the process heat, Q dot P out, simply by substitution of the values which we have calculated here for the mass flow rate, and also we have H4, H5, and H7 simply by substitution. These the values for these parameters in this equation, we can calculate the Q dot P out, which is 26.2 megawatt. Next, we will continue our discussion about another modification for the vapor power plant, which is a combination between vapor power plant and gas power. Later, we will see about that.